Yes, thank you very much. Now it's on, yes. Thank you very much. So yesterday what we did was to have a review of conventional superconductivity and the history of superconductivity, and also review the BCS microscopic theory. And today what I would do is I would like to go into unconventional superconductivity, and I will start by giving, in fact, some very general remarks about the role of the Pauli principle in these Cooper pairs. We will see that depending on the symmetries that we have in the system, we always have to fulfill the Pauli principle. This is going to give us some constraints about the symmetries of the order parameter. And then I will go about alternative mechanisms of superconductivity other than electron-phonon coupling, the microscopic description, and then show you an example. And I have chosen the iron-based superconductors because there also we can link into topological superconductivity. So let me start with general remarks about pairing and the Pauli principle. So let's assume that we have a system which is basically one band. So I have only one orbital that is important at the Fermi surface. And I have in my system inversion symmetry and time reversal symmetry. Now, what we know then is that if we have time reversal symmetry, is that the states k up and minus k down are basically related by the time reversal symmetry. So this is the Kramer's, also called Kramer's doublet. And therefore, the superconducting interaction is going to be maximized by pairing degenerate states. So by following now BCS, this is our pair wave function. So we are going to play with the fact that we have these degenerate states in order to build our Cooper pairs. Now, if on top of this time reversal symmetry, we also have centrosymmetry, so parity, then it means that the states that are k up, so k up and minus k up, they are as well degenerate. So we have four states that are degenerate. If in our crystal, we have time reversal symmetry as well as inversion symmetry. So on the other hand, the general pair distribution, I'm not talking about distribution function. So the general pair, Cooper pair wave function must obey the Pauli principle. We are dealing with fermions. So that means, if you look at the indexes, that B of minus k sigma prime sigma has to be equal to minus B of k sigma sigma prime. So we have when we do the exchange of the two spins. And this, of course, is setting some constraints in this condensate Cooper pair. So that means if this condensate is even on the k minus k, then because of the Pauli principle, I'm going to have that this should be odd on the spin exchange, so I will expect to have a singlet Cooper pairing. On the other hand, if this condensate is odd by basically doing the transformation from k to minus k, now enforcing the Pauli principle, we're going to expect that we will have that this Cooper pair is even on the spin exchange. And we may expect spin 1 triplet states. So we see already by playing with the symmetries of the system, we already get a lot of information about the symmetries of the order parameter that we expect for our Cooper pair. So now let's go back to our gap equation, where I am putting now here the most generalized form of this gap equation. So if you remember, we derived the gap equation by doing a mean field approach, where this, in fact, is what we define as our gap equation. It gives us our gap. And in putting all the indexes correctly, we have that this is a function of the pair potential glue and the condensate. So it's basically the sum over this product, where one has to be careful about taking into account all these indexes. So now let's look at the generalized gap equation, and let's consider also the properties that we have in our Cooper pair, not only the spin degrees of freedom, but we also have the orbital degrees of freedom. So if we now analyze what kind of properties can these orbital degrees of freedom give us to our Cooper pairs? So let's consider again this assumption that we have in BCS, that we have the pairing is happening. So basically, these Cooper pairs is in the energy range is around the Fermi level, and the thickness of this around the Fermi level is given in the mechanism of an electron-phonon coupling, for instance, by the omega frequency, so by the omega dBi, the dBi frequency. So now what we can do, of course, is we can do an expansion of this condensate into harmonic, in an harmonic expansion, and we can do that both for the Cooper condensate as well as for the pair potential, and we plug it into the gap equation that we have here. We just plug this expansion, and then one can see that, in principle, I can get information about possible orbital states larger than L equals 0. So for the conventional BCS, we were considering that our pairs have a total spin equal to 0, as well as a total orbital momentum equal to 0. So we were really in the most symmetric type of order parameter. So now what it shows, this expansion here, is that in principle we can still use this BCS gap equation to also describe possible expansions, so possible other type of symmetries than the S equals 0, L equals 0. So here we could think about going into higher orders. And this in L, and this is what it's called non-trivial superconductors, when you have a Cooper pairing where either the spin or the orbital quantum number is larger than 0. So summarizing now these general remarks about the role of the Pauli principle in the Cooper condensate, and considering that I have a system that it's not only limited to one band, so multiband systems, this is in fact especially important for iron-based superconductors, where we know that there the superconductivity is influenced by many, so all the iron D bands that are near the Fermi level. So therefore, in this generalization, by imposing this Pauli principle, we have that, summarizing, if the Cooper pair is even on the k minus k, then we will have that the possibility of having a state, a Cooper pair, which is a singlet and is even under the band exchange or the orbital exchange, or is even on the spin exchange and odd on the band exchange, just to fulfill the Pauli principle. And on the other hand, if bk is odd on the k to minus k, and imposing the Pauli principle, it means that we can have the option of having a triplet superconductor with an even in the orbital channel, while it can be odd, so a singlet in the spin channel and odd in the band channel. So these are all the options, and depending on the system that we're dealing with, one can go through all these options that are in fact determined by the symmetries of your system. Okay, so now this was now just to show you that symmetries play as a very important role in superconductivity as it plays in the normal state of systems. But now we want to go a little bit more in detail into alternative mechanisms to superconductivity. So yesterday we were concentrating on the electron-phonon mechanism, and this is how we were defining conventional superconductors. But we saw also all these examples that we have, many of them, where an electron-phonon type of coupling is not satisfactory to describe the superconducting state, especially because many of the materials I was showing were either Mott insulators in the parent compound and in general strongly correlated systems. So in fact, there is a very nice work from 65 from Kohn and Luttinger. So, and we're talking about 65, so it was a time where still basically the conventional superconductivity was the most dominant concept, but they were thinking about alternative mechanism of Cooper pairing other than an electron phonon. So they were thinking about, well, could just consider an electron-electron interaction become also an attractive interaction and be the origin of superconductivity? So in fact, what they did is they considered an electron gas without phonons and only repulsive interactions, and in fact, they showed that it can be a superconductor. And how can this be? So basically, they were using the concept of the fact that when we have electrons in a solid, we have that the Coulomb interactions are screened. And you know that the way the screening goes is by following the Friedel. So how the Coulomb screening goes as a function of distance, it follows the Friedel oscillation. So it has an oscillatory behavior. And in fact, just by plotting here, sorry, I forgot to put, so this is V as a function of R. You can see that these Friedel oscillations have an attractive part. And that's basically what they were seeing, that in principle, you can avoid, so the electrons avoid the repulsive part of the Coulomb interaction in space rather than in time. So you can define a mechanism where this repulsive interaction is avoided not in time. So remember that yesterday, this electron-phonon coupling, it's very important, this retardation effect. So you have an electron that distorts the lattice and goes away, and then the second electron fills the distorted lattice and therefore feels this effective attractive. Now we are not talking about an interaction in time, but we are talking about an effective interaction in space. And in fact, what happens is that the type of pairing that you expect here, due to these oscillations, Friedel oscillations, is that it's going to be in a very high angular momentum channel. So we just saw this harmonic expansion in the orbital degrees of freedom. So we are going to expect that the pairing is going to be in a high momentum channel. So now if you basically introduce now this mechanism into these equations that we had in the BCS, and this was a question also yesterday, in principle we could put another mechanism that it's not electron phonon because the equations are still valid. So if we put, in fact, this type of mechanism, then what happens is that the predicted critical temperatures are extremely low. So you see it's a power of L exponential minus L to the 4. So this was a little bit, disappointing that such a mechanism would give you very, very, very low TCs. However, this work opened this new paradigm, thank you, where in fact we are not thinking about a retarded type of effective interaction, but we are thinking about an interaction that is avoided through space. Now, there were, yes, question?
Yeah, sorry, how does screening cause the sign of the potential to just totally flip? I see that it modulates something, but I wouldn't expect it to totally flip sign.
Yeah, so when you calculate, when you do this screening, so basically you calculate this potential as a function of your electron cloud, and you assume that you have an electron distribution in space, then you have exactly this. So there are regions where there is a strong repulsion, and then there are regions, depending on the distribution, on your electronic distribution, there are regions where you have this oscillatory behavior. And you can So your question is, why do I call this positive? So you think the zero here and then positive and negative. So the way you have to think is that the way where you have the concave, it acts as an attractive potential, and the way where you have a convex, it acts as a repulsive potential. This is the way you have to think about it. And you have this because of the distribution of your electronic distribution in the crystal.
You only look at the electrons, not the ions of the crystal itself.
You look at the electrons, yeah. So you look at the screening effects of the electrons. Of course, you also put your lattice. So if you can also include if you include your lattice, you also have your positive charges there, and then you calculate the screening of your electrons in the lattice. Okay. We can talk about that later on. Yeah.
Is there an intuitive way to see why TC should be proportional to the Fermi?
Intuitive way.
Yeah.
Well, it's because if you write this potential, also as an expansion, you will see that basically these tails here correspond to very high angular momentum. I didn't put it here. Oops. So that basically you have to you do an expansion of your potential, and if you have your electrons, in order to compensate this, in order to avoid this repulsive interaction, the only way is that they have an L which is larger than 0, because then you are not going to. But if they are very fast, that's what it means. If a larger L, it means that your electrons are going to be very fast. Then they are able to avoid each other. But I don't. I should show you the derivation of this L.
Yeah, but what interests me more is why TC. I mean, the way I understand this expression is that also the larger TF, the larger the TC, right?
Yeah.
So I don't see how this follows from what you just said. Sorry.
Okay.
Yeah.
So what the way you obtain that is that you put the information of your potential in. Okay, so let me go back. This was the gap equation, but if you remember, we can derive out of this gap equation, we can derive then also the TC. So here is where you go. Here is where you have what you are thinking as about your attractive or repulsive, but this is the effective interaction between your electrons. So what you do now is you put here this interaction that I'm showing as a function of R, and you expand it as a function, so in this way.
Okay.
And this gives you these higher order L terms that are the ones that are the dominant ones in the expression of the TC. So it comes from doing this expansion in your repulsive Coulomb interaction, screen repulsive Coulomb interaction. Okay.
So I guess the higher TF is, the more, I don't know, terms I will have in that, like sum over K.
You go on having higher orders in your expansion.
Okay, thank you. Yeah.
More question? Okay, so let me tell you another mechanism, which is in fact the mechanism that is being mostly used and discussed for the unconventional superconductors. And this is a suggestion by Berg and Schrieffer in '66. So you see it was, so there was this one theory, BCS, but there were many other suggestions about, or scenarios, because this was a new state of matter, so it was important to understand where the origin of this new state of matter comes from. And basically what they were proposing is pairing by magnetic fluctuations. So again, we completely neglect phonons, and you can think about this type of pairing is, imagine that you have your electron has a spin, and polarizes the medium around it magnetically. So the second electron just feels this polarization, this magnetic polarization from the first electron, and feels the attraction by magnetic interactions. And this is, in fact, so let's say what a natural type of pairing that you would expect when you have this type of phase diagrams for your systems, when the system, for instance, is, as we were showing in many of the superconductors, that the parent compound is antiferromagnetic, so it has a long-range magnetic order, and then by doping, so by introducing some charges into the systems, of course, the fact that it has a magnetic order, it means that it has a strong magnetic fluctuations, so they will be important in order to define which state you have. So this, the idea with this type of mechanism is that these magnetic fluctuations, spin fluctuations, can also be responsible for a Cooper pairing. So you basically use the fact of the existence of spin fluctuations not only for creating a long-range magnetic order, but also for possibly creating a superconducting order. And this is what one usually compares with. So one talks about spin fluctuations that promote magnetism or at some critical, for instance, doping or pressure, then these spin fluctuations promote superconductivity. So these are two types of order that are competing, but with the same origin, which are these spin fluctuations. So this is the idea behind this type of pairing, which is very much, in fact, used for unconventional superconductivity. Questions to that? Okay, so let's now go back to our gap equation for unconventional pairing, where now here we are going to, in principle, so we can have as the origin of this V, we can now include one of these suggestions in order to, that I was showing, so two of them, but there are many, many works that I'm not mentioning here, but superconductivity is a big, big, big field, and there is a lot of important papers that with the time, I cannot mention all of them, but definitely there has been a lot of work done to understand this state of matter. So what I'm doing now here is let's analyze now again our general BCS gap equation that we derived within the BCS formalism. And now let's make basically some assumptions on this interaction between the electrons. So now what we saw in BCS, that this interaction was the effective electron-phone interaction, was attractive, and therefore this equation had a solution because it was attractive, so it was negative, and then you have a solution which is non-trivial. Now, let's assume that, that this interaction, first case, is local and in real space, and it's repulsive. So what happens if it is repulsive? Of course, this is positive, and therefore, because you have this negative minus sign here, there is no solution. So just a repulsive interaction is not going to give you, if you now assume that you have a valid BCS gap equation, is not going to give you the order parameter of your system. Okay, so now let's go now to the very extreme case that we have very strongly correlated electrons, and let's assume now that we have a strong interaction between nearest neighbors. And this is the typical case that we can use for the cuprate material, so the copper oxide system that I was showing to you, where basically the lower energy in this system is determined by the coppers sitting on a square lattice. And we have a half-field case when the system is antiferromagnetic, and we just dope the system and become superconductor. So now what we are assuming is that the interaction that we have in our electrons sitting on a square lattice is given by just nearest neighbor interaction given by this cosinus. Kx, Kx, Ky would be the corresponding k vectors for electron 1, and k prime and y and k prime x would be for the electron 2. And this is a repulsive interaction. So this is now the description of a correlated system with such a repulsive interaction. So now let's look at, again, whether we find solutions to this gap equation now with such an interaction. So now what we see is that we can, you see that we have here a sum over all the k's in the Brillouin zone. So in this sum that we have, I will show you the example in the next slide. So basically what we follow is along, remember that these sums are always along in a thickness around the Fermi surface. So let's assume the case that we have that our one electron is at k, and the other electron, k prime, is at pi pi. So A is the lattice spacing. So if we have these electrons, one at k and the other one at pi pi, then what we see is that if these two gaps here, the gap at k and the gap at k prime, have opposite sign, then we have a solution to this equation. So which is what we are seeing here is that we can find solutions to a repulsive interaction if we have change of sign by basically going to different k's in the Fermi surface. Let me show you that for the case I was telling you for these cuprates. This is basically what I was explaining. So what I'm showing here is the Brillouin zone of these cuprate materials in a two-dimensional, so these materials are very two-dimensional. So this is the two-dimensional Brillouin zone of this square lattice of the copper sites. Now, the Fermi surface in this system, when I am a little bit away of half-filling, when the system becomes superconductor, is shown here. This is the Fermi surface that I expect for this square lattice. And now what I was, and remember that we are building these Cooper pairs, that they are basically near the Fermi surface. So basically I'm putting my states here at the Fermi surface, and I'm doing, so a way of looking into this Cooper pairing is by thinking about scattering. So basically what I do is I want to build this Cooper pair that are at this position. So one is at the position here, and the other one is going to be at pi pi. This is the what I was showing to you. So what we saw is that this type of states where they are basically, this is where they have this interaction given by this term here, then what we saw is that we can have a solution of this gap equation if I have a change of sign of the gap function going from one k point to the other, so between the two k and k prime. So if you have to have a sign in this function, it means that you need to have somewhere a place where this gap function goes to 0, because you want to go from positive to negative, so it has to go to 0 somewhere in your Brillouin zone. And this is what we call the nodes. So you have a gap, so you can circumvent the electronic repulsion by having nodes in your order parameter. So what I'm doing here is basically the gap gives me, in fact, the symmetry of the order parameter. So what happens then is that what we are going to expect is to have nodes along these diagonals. This satisfies that the gap function changes sign when I do this Cooper pairing between a pair of electrons that are at these opposite sides of the Fermi surface. So, and this is what we call the D-wave pairing, and in fact this has been observed in the cuprates. The order parameter of these materials is a D-wave pairing, where indeed the gap changes sign, and you have these nodes along the diagonals of the Brillouin zone. And this has been observed experimentally very nicely, how this, you find these nodes, and it's called D-wave, so one gives to these order parameters, in fact, a nomenclature which is inspired by the nomenclature that you know from orbitals, but it's not an orbital. It's an order parameter, and it has the symmetry of a d orbital. So if you remember that the orbital is this flower, so it has this flower shape, and therefore that's why it's called a d-wave pairing. And you can, so let me now go to a second example, where here in the cuprates we had only one band, so the Fermi surface was basically defined only by this. This Fermi surface comes from the copper dx squared minus y squared band, which is the one that crosses the Fermi surface. But now let's go to another family of superconductors, which are these iron-based superconductors. Here, these systems are less correlated than the cuprates because they are never Mott insulators, so they are always metals. However, even if you can treat this system not having to invoke very strong correlations, it has another complication. And the other complication is that it is a multi-orbital system. So you really have to include all the d orbitals of the iron, because you see this is the band structure. So you have all these d orbitals that cross the Fermi surface. So the Fermi surface is defined by various sheets that correspond to different band character. So here, let me show you, this is the Fermi surface. Again, if you project in a 2D plane, so this is the 2D kx, ky plane, this projection is in fact, again, a square lattice. So you have a square lattice of iron sitting on the vertices of this square lattice, on the sides of this square lattice. And now the type of, if you just follow, here is your Fermi level. If you just follow to draw the Fermi surface, you see that around the gamma point, you expect to have two Hall pockets, while here around the X point, you expect to have electron pockets. And this is what you see. This is the gamma point. Sorry for having forgotten to write the K points. So this is the gamma point, and you have these Hall pockets around the gamma point that you can see are of different band character. And then you have, at the X points, these electron pockets that all, can have also different band character. And here I didn't say that, but the word nesting, I didn't use it, but in fact this is inherent in this system. So in the cuprates, the previous case, when we are exactly at Hall filling, we do have a perfect nesting. So then the Fermi surface looks like that, and we do have a perfect nesting. And perfect nesting means that, that it costs you zero energy to scatter your electron from one side of your Fermi surface to another side. That's why what we call perfect nesting. And perfect nesting, then, it's telling you that you will have an instability. So it's another way of understanding this antiferromagnetism. So if you have perfect nesting at Hall filling, for instance, in the cuprates, but it's also the case that I was showing to you, then you have a strong instability because the electrons basically, it costs them no energy to do this scattering from one side to the other side of the Fermi surface. So it means then that you are going to expect some kind of instabilities. One instability is that the system orders, and this you can explain then antiferromagnetic order, if your nesting vector is of this type. But you can also have superconductivity when you dope a little bit, which is what is shown here. So for the iron-based superconductors, you also have this perfect nesting. The nesting is, though, between the Hall pockets around the gamma point and the electron pockets around the X point. And this is, in fact, why you can explain that the system has a charge, not a charge, it's a spin density wave in order to sort of circumvent this instability of a perfect nesting. So we do have this. So now the question is, how do we build now our Cooper pairs? So I'm not talking about the magnetic state, but I want to talk about this superconducting state. Okay, so it's a correlated system. So it's near magnetic state. So I'm going to expect also that this mechanism with spinning fluctuations is going most probably to be the one that drives the system superconductor. So I'm going to expect, again, a repulsive interaction. So again, if I have a repulsive interaction, the question is, how can I get a superconducting order parameter from a repulsive interaction? Now here, we have a different Fermi surface than in the cuprates, because here you saw that the Cooper pairs, you are going to build this kind of Cooper pairs. You can build them between your hole pockets and your electron pockets. And moreover, they are, so sorry, the difference between this Fermi surface and this one is that one is the folding of the other one. So that's, it is whether you work in the so-called 2 iron per unit cell, which is the physical unit cell in these systems, or you unfold this 2 iron per unit cell and you work in the 1 iron per unit cell. So this is the 1 iron per unit cell Fermi surface, and this is the 2 iron per unit cell. Or you can, did I say it correctly? Yeah. So now what you have here is you build your Cooper pairs between these electron and these hole pockets. And they are also of different band character. They can be of different band character. So you can see that you can, in fact, again, if this is repulsive, you will favor the formation of a gap function, so of an order parameter, if you change sign between the gap here, for instance, at the hole pocket, and the gap at the electron pocket. So that means you need a gap that changes sign when you go and do this kind of Cooper pairing. Now, the difference between the Cooper pairs here is that you are dealing with different types of pockets, so with electron, with hole pockets. And therefore, you can still keep your S wave. You don't have to go through a node to have this change of sign between positive and negative. And this is what we call the S plus minus wave gap, that it shows, in fact, full spherical symmetry, the gap function, but it doesn't have nodes. And it doesn't have nodes because I can play with the fact that I have that I have these electron and hole pockets and multi-orbital. So this is, in fact, one of the first persons to realize about this S plus minus was Igor Mazin, while trying to find the order parameter for these systems. Okay, so now what I was showing is a little bit how, before we do a calculation, we try to extract information about the possible superconducting order parameters that we may expect in the system by, as you saw, just looking at Fermi surfaces and the symmetries of the system. But now we have to do a calculation. So now it's time to do a little bit of predictive power. So what can we say about this superconducting state? What can we say about the thermodynamics of this superconducting state? And all these nice properties that we saw that with PCS, they naturally can be extracted. So we have a correlated system. Then let's, the same as we started for BCS, by having a model where we included this attractive electron-phonon interaction, now our starting point is going to be the Hubbard model. So this is the minimal model I can think of to describe electrons that have correlation. So basically that have a kinetic energy, and then the most simple way of introducing Coulomb repulsion is by introducing an on-site Coulomb repulsion. So if we now do the Fourier transform of this Hamiltonian, in momentum space, it has then this shape. And this is just a representation of basically this model that we need to pay an energy U if we have two electrons on the same side. Now, since we are interested in all these superconductors that I was showing to you, where we have this magnetism which is basically neighboring superconductivity, so in principle, we start with a scenario that we expect that the spin fluctuations may be the ones that are promoting the superconductivity in the system. So, and if it is the spin fluctuations, what we believe, or believing it's not good to say it in physics, but what we think that, although we say it a lot, but that we think that this is the mechanism, then of course the magnitude that is very representative of a spin fluctuations is a magnetic susceptibility. So already by analyzing the magnetic susceptibility in this system, we can then extract the information about, and this is what I'm going to do, about the superconducting state. So therefore, we need to calculate, and now calculate, susceptibilities. So here I'm showing the transverse spin susceptibility, which corresponds to this correlator S plus minus, so basically S minus at a minus Q and time tau, and S plus at Q and time tau. So it's basically a correlator that we need to calculate. So if you now go to the Matsubara frequencies, you can calculate this correlator in the case of U equals 0. So this is the so-called non-interacting susceptibility. And you can, in fact, diagrammatically represent this susceptibility, in fact, as this bubble. This is the non-interacting spin susceptibility that describes basically a convolution of two Green's function. So this is the first step. Always we have to start with a non-interacting case. Now let's go to the interacting case. So what changes when we switch on interactions? And now, of course, my interaction is an on-site interaction. So what we are doing a lot is random phase approximation. So basically, it's an expansion in the an expansion of this interaction term that, in fact, gives you a series of diagrams that you can sum up. And this is what we are going to do here. So basically, I'm doing now here random phase approximation. So let's go on just writing the diagrams that we expect that are going to contribute into this interacting susceptibility. So of course, this is our bubble, the non-interacting one. The next would be that you are basically connecting two of these bubbles. But you see already that you have, you can skip many of these diagrams, like this one, because if you look at this one, it contains this type of vertex. So it means that the U would do a flip from up and down, and this is not what U does. So you can just get rid of these diagrams, and the diagrams that you have, it's for instance here, the electrons have a scattering through the Coulomb repulsion, and then you have basically various scatterings that you can include, and you can indeed sum up this series. And this series, and this is what it gives you in these random phase approximations, which is what we say it's a sum of these bubble diagrams. It's, of course, an approximation, because you are not considering all possible diagrams at all possible orders. But it has a subset of diagrams that you believe, again, the word, that this is going to be maybe the most important contribution. So when you do this type of sums, whatever you are calculating, so here we are calculating susceptibilities, but also if you calculate the screen-Coulomb interaction also in this type of approximation, it always has this kind of shape. So you see it is basically a quotient of the non-interacting susceptibility, and in the denominator you have this 1 minus your interaction, which our interaction is u, and then the non-interacting case. So this is the typical form of any magnitude that you want to calculate within the RPA approximation. So now, of course, what is interesting is that this interacting susceptibility has a divergence, as you see, when this goes to 0. And this divergence is the one that, in fact, is related to what you are going to expect in the system to have a magnetic instability. So if you do that for the square lattice I was showing to you at half filling, it gives you the magnetic instability precisely at pi pi, which is, in fact, the antiferromagnetic order, which is what we know that happens in the cuprates when they are half-filled in the parent compound. So what it tells us is that with this kind of calculation, already we are going to have information about where are our instabilities. And this is going then to come into the equation of our effective interaction. So the spin fluctuation exchange, now this would be the vertex. I'm jumping very much, but stop me if you have questions. So this would be so now I want to calculate the superconducting vertex. So the one that defines, I have basically, and here I'm showing the case of the singlet, I have an electron with a spin up at K, an electron with a spin down at Q, and then they interact through this effective pair interaction, whatever it is, whatever gives this interaction, and then we have the creation of the two Cooper pairs at a state K prime up and down. So now we can schematically show if our effective interaction is this Coulomb repulsion. Then we can express this type of interaction as we were showing schematically, that you have very many scatterings between your electrons, and you can sum up the series, and you get that your effective interaction between your two electrons that are going to form the Cooper pair, as you can see, is directly related with your magnetic susceptibility. So this is because we took as a scenario that the origin of the mechanism is these spin fluctuations. I don't know how much I'm doing with the time. 10 minutes, okay. So this is now how you write it, in fact, a little bit more rigorously. So within this approach of the spin fluctuation, basically what you have to calculate that you will plug then into your gap equation, because the microscopics in your gap equations is all embedded in this potential. So this is what you are calculating macroscopically, is this potential. In the BCS, you were calculating this potential was your electron-phonon coupling. Here, this potential, we are calculating it in terms of these interacting spin susceptibilities. So this is basically how we describe this pair potential within this random phase approximation. So it's basically, it has to be a two-particle vertex function. And here you see a lot of indexes because I just wrote this pair potential also in the case that I have multi-orbital cases, like in the iron-based superconductors. So these are orbital degrees of freedom, PQST. And then, of course, you have an electron orbital P, spin sigma, K, which is pairing with an electron orbital T, or scattering, with opposite spin and momentum minus K. Then this is the effective interaction, and this is now the creation of the new scattered electrons that should form your Cooper pair. And just to give you a flavor of the kind of diagrams that we are dealing with, I'm showing here for a multi-orbital Howard Hamiltonian, basically which are contributions to the first order in the interaction. So if we have a multi-orbital Hubbard Hamiltonian, we not only have this U interaction, but we also, this would be the intra-orbital intra-site, but we also have an inter-orbital Coulomb repulsion, inter-orbital intra-site, and we also have a Kunz coupling. So this is a very important new scale that comes into the system in order to describe the correlated nature of the system. So now what I'm showing here is a subset, these are not all, but a subset of diagrams that contribute to this vertex function, which is the one that is going to give me the pair potential, where what you see is you have the scattering of your two electrons. This is the propagator. Here it corresponds, or the origin of the interaction. This is meant for when it is through the U. This is meant when it is through V, and this is meant when it is through J. And I don't show you second order because it becomes very complicated, because you see, you have to, I mean, there is a systematic way of doing this diagram. So basically, you have to calculate your expectation values and then do big theorem, and then you transform this set of expectation values with big theorem into these diagrams. But this is basically the calculations that you do. And once you have done that, then you are set. So here is, for instance, just for a simple case, if I forgot about multi-orbitaliticity and I have only one orbital, then, and I am concentrating that I am only interested in a singlet channel, so basically an effective S equals 0 interaction. Basically what you have is contributions from what we call different channels. So the triplet channel is attractive in that case, and the singlet channel is repulsive, so you have to sum all these contributions that come into your vertex. And at the end of the day, the expression looks very simple. So that's a nice thing when you do RPA. We also do other type of approximations, but this is better approximations than RPA, but this is good enough. So you see again here, when you have all these diagrams, the final expression that you have for your total pairing interaction is very simple, and you recognize again, so here is your, I'm doing the one band, so it's only the Hubbard interaction that plays a role. But again, you see here your susceptibilities. This is the spin susceptibility that has this random phase type of form. And this is the charge susceptibility that is given by this term here, that also have a random phase approximation type of form, because what I'm doing simply is by summing all these diagrams that I was showing to you. So once we have that, we plug then this, which is all now microscopic, so this is all the microscopic information, we plug it into the gap equation. In fact, we do the linearized gap equation, and we extract that information, for instance, of the order parameters. So let me show you an example. I don't know how much time do I have? 5 minutes. Let me show you an iron-based superconductor, just to see how this goes in real life. So, and I chose this potassium iron 2 arsenic 2. This is what it's called the extreme hole-dope case of the iron-based superconductors, because this cation here is a 1+ and not a 2+. So that means that I'm going to basically the Fermi, so I'm going to have no electron pockets, so I'm only having hole pockets. We will see that in a moment. Now, what is interesting about this material, this is temperature as a function of pressure, is that if you press the system, you have two, at least this is what was reported some years ago in experiment, that one would observe superconductivity really going up at a given critical pressure of 15 gigapascals with a rather large TC with respect to the TC that you have in the ambient pressure. And the question was, what gives this shooting up of the superconductivity? and whether these correspond to superconductivity of different nature. Now, what we know that happens at these pressures is that there is a volume collapse in the system. So what happens is when you press the system, you see here, these are arsenic atoms, and basically you have pz orbitals that are phasing like that. So if you press the system, what happens is that there is a critical pressure where these pz's really overlap, so you have a binding anti-binding type of response, and therefore the system goes into a lower and lower energetically state if just compresses along the z direction, and this is the collapse phase. So what we did is we analyzed the superconducting or the parameters in the superconductivity by using this method that I was showing to you. Now what I want to show here is only the Fermi surface. So let me show you the Fermi surface in this collapse phase. By collapsing, what you regain is this small electron pocket. So you have the whole pockets. This is basically, you see it's not a completely simple type of Fermi surface. You have many different type of band characters here. But what I want to show you is the comparison between this system and this system where you don't have this whole pocket in the middle. Now, when you calculate superconductivity, remember that what we were doing is calculating the susceptibilities, which already finding the instabilities in the susceptibility gives us information about what kind of Q vectors are going to define which instabilities. And I'm just comparing these two systems because this is non-superconductor and this is superconductor. So you see here, and this by just drawing the different components, this is the susceptibility we calculated shown in the Brilling zone, that there is an important peak here around the X point. And this important peak is in fact defining this Q vector here. And there is also a peak here, which is defining this Q vector here. In the case of calcium 122, there is no clear, apart from this spike here, which is not commensurable to the lattice, these Q vectors are not as pronounced, so there is not as much nesting. So now one can calculate with the formalism I was showing to you, which is now the gap function, and therefore which is the order parameter. And what you obtain for this system is, again, this system is an S plus minus order parameter that you can see here with the color, the change between plus and minus contribution in the order parameter. Now, what is interesting, and probably this is my last slide, is that I was showing here the calculation for this region here when we're in the collapse phase. Now, if we do the calculation for this uncollapsed phase, in this uncollapsed phase, and we do exactly the same calculation, the susceptibilities, the instabilities, and then the pair function, and then the gap function, the symmetry that you have for this case is a dxy symmetry. So the order parameter changes sign when in a dxy manner, so plus, minus, plus, minus. So what happens is that at the phase transition, indeed, there is what we call a Lifshitz transition because the order parameter changes symmetry. So you go from a dxy order parameter to an S plus minus. And this is the kind of results that you can obtain out of these calculations where we assumed that the superconductivity it's originated by these spin fluctuations. Now, this is my last slide. I wanted to show you, but I think I have no time anymore. But I wanted now to make the connection between iron-based superconductors, where we are doing all these calculations of the order parameters and the properties in the superconducting state, and trying to relate it a little bit with topological superconductivity, which is what Charlie also was also today mentioning. And there are, just to mention to you, and Vidya has also done some nice experiments on that, that there are all these materials, all these iron-based superconductors, where, for instance, in the case, so if you dope them properly, then you can put your Fermi level precisely where the system has this feature of being, basically you are here in this, at the verge of this, due to this band inversion between p and the orbitals, that you can, in principle, expect that in the surface states you are going to have, for instance, this vortex with these Majorana zero modes. And this is what Vidya, I don't know whether you are going to talk about that, so she has been observing that, and there are very nice results on that. There is a lot of discussion, especially for this system, about issues of disorder, but I think Vidya will give a much overview of this part. And the second part is that we also, so yesterday Claudia was saying topology is all over. You only have to look where you were in the band structure. So in fact, this is a proposal that we have done to take these iron-based superconductors, and on the magnetic field, you can have, in fact, manifestation of Weyl points. And this has been done in collaboration with many people, but some of them are here. So Mikael is here, and Niklas is here. So two of the students that are here, we did this work of proposing that you can also have this type of physics in iron-based superconductors. And what it would be extremely interesting is the manifestation of this Weyl physics in the superconducting state. And with that, I would like to thank you for your attention.
Like yesterday and today, you basically showed these two mechanisms. One, and like basically they take place on a different time scale, right? So you have this retarded phonon-mediated superconductivity, and then I guess the instantaneous spin fluctuation-driven one. And this other one you showed by Luttinger, like the one with the Friedel oscillation. So where do I put this? I mean,
this was a proposal, but I don't. At least I don't know of people that really followed on this one. I mean, there are many works done during that years about this mechanism, and it's very nice to see that you have this option. But I don't know of any material where one has seen a realization of that. At least I'm not aware of.
Okay, but these fluctuations are in time, right? And not in like this potential that you drew. Those are in time and not in space.
In space,
right?
This was a space.
Oh, okay.
This was these oscillations in space.
Okay, and maybe this is then stupid, but I mean, like in the analogy with, I mean, in these systems where you have like the antiferromagnetic dome in the phase diagram next to the superconductivity. Well, then, I mean, you look at the spin fluctuations.
Oh, so what are you talking about? The Luttinger-Korn mechanism or the spin fluctuation mechanism?
I mean, I'm trying to make like an analogy. So, like, if you have the magnetic state, then you look at the spin fluctuate, or like in the spin channel.
So like exactly, that's what we did here.
So if you had this like potential in space in the, I mean,
well,
why don't you have it?
This was the picture I was showing. I don't know whether this is what you're talking about, but
yeah. I mean, wouldn't you then expect it to have it in a phase diagram where you are close to the? Yeah, this is for spin, and then the other one with the Luttinger. Wouldn't you expect it to have it in a phase diagram where the superconductivity lives next to the charge density wave order? Then, if you have.
So you definitely you need a metal there. It has to be in a metal.
Yeah, I mean, I'm thinking of these Kagome superconductors, but there are people also.
No, I don't think that people are using this mechanism for the Kagome, but.
No.
But good point. Let me think about it. I don't know. Yeah. I mean, you need a metal. You definitely need a metal because you need this screening behavior. Yeah. Now, the question that you are posing is, what does a charge ordered distribution how much can influence your superconductivity.
Right, because
But
of all these
in
papers, people still do this to calculate the vertex, right?
In the Kagome, no. In the Kagome, okay, there are two types of calculations, but there is a lot of discussion now that it is an electron-phonon type of interaction, so that probably the superconductivity could be rather conventional. And then there are the works, I agree, that take in fact the Coulomb repulsion and the next nearest neighbors, and you do the same formalism and assume some spin fluctuations. Indeed, it's true. People are doing this type of calculations, even though they're in the vanadium metals, the magnetic moment is very small. But still, you are right, there are people that do this type of calculations, and in fact, we are looking into that as well. Just interesting to see what it predicts, this mechanism for these materials. But there is a lot of discussion that it could well be that it is an electron-phonon type of.
But isn't in that case the phonon and electric, it's strongly coupled, right? I mean, like this.
No. So you can have. So in fact, there is a new material, chromium diboride, that we are looking into it, where you could have the two mechanisms, and the question is, do they work with each other, or do they compete with each other? And this is what we are looking at. So there is a system under pressure. You can see that electron-phonon coupling is changing as a function of pressure, and you can see also that the system is also near magnetic state. So you may have the two mechanisms there, and the question is, do they grow together? Do they compete each other? So we are calling that hybrid coupling or pairing.
Thanks.
You can have that. Yeah. Yes. Oh, there was.
Let's wait for the microphone.
Oh, it takes a long time.
So just curiosity. So there is like a theorem saying that if I have S-wave pairing, then if I add impurities, non-magnetic impurities in my superconductor, then DC doesn't change. Anderson's theorem, whatever, something like this.
Yes,
so
yes.
I was just curious. Is this also true for S plus minus, or?
Good question. I have to see I know which theorem you're talking about, but I have to see the premises of this theorem. So what is the assumptions that you do? I'll check that. I don't know.
Okay.
I have to check, but it's a good, very good question. Yeah.
Maybe we should finish the lunch and thank Rosa again.
Thank you.